Hi everyone, now we are going to discuss about matrix chain multiplication. Here we given some matrices to multiply. You have to determine the best order to multiply them so you minimize the number of single element multiplications. So that is determine the way the matrices are parenthesized. First off, it should be noted that matrix multiplication is associative but not cumulative commutative, but since it is associative we always have. Here we need to mm, choose one option, either maybe like multiplying AB and CD individually and multiplying them their product, their result, or we have to multiply like this: CD multiplication CD and this product with B, and the result will be multiplied with A, or any other grouping as long as the matrices are in the same consecutive order, but not AB. Multiplying AB and CD is equal to B, multiplying BA and DC, like it, but we should not do like that. It may appear that the amount of work do, done won't change if you change the parenthesization of the expression, but we can prove that it is not the case. Let us use the following example. Let A be a 2 by 10 matrix and B be a 10 by 50 matrix. Let C be a 50 by 20 matrix. But first, let's review some matrix multiplication rules. Let's see the rules of the matrix multiplication. Let's go back to our example. We will show that the way we group matrices when we multiply A comma B comma C matrix. Let A be a 2 by 10 matrix, let B be a 10 by 50 matrix, and C be a 50 by 20 matrix. Here consider computing A of B into C. Multiplications for C is equal to 10 into 50 into 20, that is 10,000, creating a 10 into 20 answer matrix. Multiplications for A of B into C is equal to 2 into 20, 10 into 20, that is 400. Total multiplications is equal to 10,000 plus 400, that is 10,400. Consider the computing AB, A into B, and with that the result will be multiplied with C. Multiplications for AB, 2 into 10 into 50, that is 1000, creating a 2 by 50 answer matrix. Multiplications for AB into C is equal to 2 into 50 into 20, that is equal to 2000. Total multiplication is equal to 1000 plus 2000, that is 3000. Our goal today is to, given a chain of matrices to multiply, we have to determine the fewest number of multiplications necessary to compute the product. Formal definition of the problem: let A is equal to A1 into A2 into and so on an. Let M I comma j denote the minimal number of multiplication necessary to find the product. We need to find the minimum number of multiplications necessary to find the product. That is AI comma AI into AI plus 1 into so on aj. Let Pi minus 1 into Pi denote the dimensions of matrix AI, which must attempt to determine the minimal number of multiplications necessary m1 comma n to find A. Assuming that we simply do each single matrix multiplication in the standard method. The key to solving this problem is noticing the subproblem optimality condition. If a particular parenthesization of the whole product is optimal, then any subparenthesization in the product is optimal as well. Say what? If if the multiplication is in this way, that is A of B of CD, that is CD and F are multiplied, and this result will be multiplied with B, and its result will be multiplied with A, is optimal. Then B is multiplied with CD and EF, so is optimal as well. Proof on the next slide. Let's see. Assume that we are calculating A, B, C, D, E, F, and that the following parenthesis is optimal. Here you can see this is the optimal parenthesization. then it is necessarily the case that B of CD and EF, okay, is the optimal parameterization of B, C, D, E, F. Why is it? Because if it wasn't, and say multiplication of BC and DE, their result will be multiplied, and it will be this whole result will be multiplied with F was better, then it would also follow that. Here we can see the parameterization of A and multiplication BC and DE and F was better than A of B and CD E F. Our final multiplication will always be of the form A1 into A2 so on AK into AK plus 1 into AK plus 2 so on AN, and this both result individually multiplied with each other. In essence, there is exactly one value of K for which we should split our work into two separate cases so that we get optimal result. So here is a list of the cases choose from. A1 into and A2 into A3 into so on AN, or A1 into A2 into A3 into A4 into so on AN, A1 into A2 into A3, this result multiplied with A4 into A5 into so on AN. Like that we increase the number with, and we'll multiply the result individually, and we will multiply the result with result again. Basically count the number of multiplication in each of the choices and pick the minimum. One other point to notice is that you have to account for the minimum number of multiplication in each of the two products. Consider the case multiplying these four matrices: A 2 by 4, B 4 by 2, C 2 by 3 and 3 by 1. A is multiplied with BCD. This is 2 by 4 multiplied by 4 by 1. So 2 into 4 into 1, that is 8 multiplication. So plus whatever work it will take to multiply BCD. Here 2 AB multiplied and CD, and this result will be multiplied. This is 2 by 2 multiplied by 2 by 1. So 2 into 2 into 1 is equal to 4 multiplications. And ABC into 2, this is 2 by 3 multiplied by 3 by 1. So 2 into 3 into 1, that is 6 multiplications. This leads us to the following recursive formula. The recursive formula is mi comma j is equal to minimum value of mi comma k plus mk plus 1 comma j plus pi minus 1 pk pj overall valid values of k. Now let's turn this recursive formula into dynamic programming solution which subproblems are necessary to solve for. Clearly it's necessary to solve the smaller problems before the larger ones. In particular, we need to know mi comma I plus 1, the number of multiplication to multiply any adjacent pair of matrices before we move on to larger task. Here this is the algorithm which we use to in matrix multiplication. Here we given the order, that is like A by B like that, and we will find the minimum the order minimum multiplications which we need to get the solution. Basically we are checking different places to split our matrices by checking different values of k and seeing if they improve our current minimum value. So you can see the figure, this is showing the whole problem. The M and S tables computed by matrix chain order for n is equal to 6 and the following matrix dimensions. You can see this in that figure. This M2, 5 is the minimum one, and in that 2, 2, 2, 3, M2, 4. These are the results, and in that the minimum value is 7125. So that is the answer. Thank you.